All right, hello everybody. Welcome back to this week's EECS education section. Today we're going to be talking about real components and some of the things you have to deal with when you actually put real circuit components into your projects. Um, Capacitors, inductors, and resistors are all things you're probably somewhat familiar with, but when those things are actually put into a real system, how do they actually behave? Also, batteries, will be covering some of the real aspects of batteries. So jumping right into it, um, just a general overview. Ideal components, it's all sunshine, rainbows, and puppies. Compared to or real components, that is. Real components, as you can see, will have you crying or laying on the floor. Um, so this is just sort of, there's a lot of things and a lot of complexity that will be added here. So it's always good to make sure you keep things in an understandable sense. So however that helps you guys, if that's writing it down, or we're probably going to be doing a lot of whiteboarding in this education section. So please just ask a lot of questions. It's going to be scary at first, but hopefully this can help you through that. So Um, just a, I forgot to put a summary slide in here, a quick summary. We're going to be going over capacitor non-idealities, and that gets a little bit into some things about inductors and some things about resistors, but mostly we're focusing on capacitors today. And then at the end, we're going to cover batteries and their non-idealities a little bit. So to start us off, this is what you may think a capacitor is, right? But in actuality, in order to keep things simple, I'll just show you the model. We can go more in depth on how that's actually derived later. Um, but in actuality, that is what a real capacitor looks like in terms of ideal circuit components. So within a capacitor, right, you have all these layers on top of each other. So there's some ESR, equivalent series resistance, in the capacitor because you have the resistance of all the copper and conducting layers in that capacitor. There'll also be some R leakage. If you hold a constant voltage on a capacitor, some current will leak through. It's not going to perfectly hold that voltage. There'll be some current going through. But in the center, you do have this ideal capacitance, and that's the actual like farad rating that they give you in the data sheet. Um, and also you have this equivalent series inductance or ESL. Um, that is from the trace inductance going into the capacitor. So that one's a bit more complicated. And I think we get into that on the next slide. So all of these are coming from real physical aspects of the capacitor. And sorry, I don't have any diagrams on here to actually show you physically where those are coming from. This is more of a high level. We can go into manufacturing techniques in another education section. But starting off with the equivalent series inductance, I'm just going to be talking about the main effect of this so that you guys know what the effect is, so that when you start testing your boards and you start working with things, um, like we're doing a lot of bring up right now, right? I want you to be ready for that. You can, maybe you'll identify something that's wrong with the board that is caused by this. So capacitors, they have equivalent series inductance, right? And when you have a inductor, resistor, and capacitor in series, you've made a resonant circuit. So this graph shows three different ESLs and how that would affect the resonance of your circuit. But essentially what happens is as your frequency is increasing, right, our capacitance is going to decrease. And the reason that is because, here, let me pull up a pen. Um, yeah, so capacitance, if you write it in like the complex domain, is 1 over J omega C. Apologize for my handwriting. I'm doing it on a trackpad. Um, so this is what like the impedances. So as the frequency increases omega, this value is going to decrease. And that's what you see at this first part of the graph. And then because we have an inductor in series and the impedance for an inductor is j omega L, so impedance actually increases with frequency. So that's what causes it to go up on the other side. And when you have a resonant circuit like this, this peak down in the middle is actually at the frequency 1 over square root LC. So that's like quick math you can do to find the resonant point of your circuit. And how deep the point of that resonance is, that's dependent on your equivalent series resistance. Now, all the things I'm saying are not specific to this implementation. This is true for any inductor, resistor, capacitor in series. But this specific effect is caused when you have the, like it appears in this instance as well. Now, the reason it goes down and then comes back up is because if you imagine at these lower frequencies, your at lower frequencies, your impedance over here on the inductor is going to be really low, right? Omega's low, L is constant, so this impedance is low. And omega's low over here, so your impedance of the capacitor is going to be really high. So the capacitive term dominates. Then as you get higher and higher, these terms start becoming similar in size. And then after your resonant point, then the impedance of the capacitor is so small that it's really the term of the inductor that's taking over. So what does this mean? A lot of implementations of capacitors have some type of switching on them, such as switching power supplies, or if you have a decoupling capacitor on the power rail of your MCU, then that MCU is switching at some frequency. It has some internal clock. If that clock frequency is too high and you go beyond the resonant point of the ESL, then you could actually be putting an inductor into your system, which is not good. So if anything's like acting funky around your capacitors, you're going to want to make sure first that like the frequency is okay. You're not dealing with super high frequencies. Now on our car, nothing really operates at too high of a frequency. Everything's fairly standard. We're not pushing boundaries on high frequency applications. So typically you're okay, but this is a very important like phenomenon to be aware of. Are there any questions on this phenomenon or like what its effects are? All right. Um, Next is, well, let's talk about ESR. So the equivalent series resistance. So like I was saying before, a really common spot for capacitors to be are in switching power regulators. And we'll have another lesson either next week or the week after where I'll talk about the different types of switching regulators. But there's three main ones. There's a buck, a boost, and a choke converter. So this is the topology for a buck. Don't need to get too in depth into this. Like I said, we'll do it in like a week or two. Um, but basically, you have a switch, and this turns on and off at some frequency, and that's how you set the ratio of your input to your output. So this causes a ripple on your output, and the ideal ripple, if this capacitor was simply just a capacitor, looks like the top graph on the left. But when we have this equivalent series resistance, as we have current going into the capacitor, there'll be a voltage drop across that resistor, right? So that's actually what this increasing one is, you have current going over that resistor. So the voltage is higher, right? Because current is going here. Let's draw the ESR in there. You have the ESR here. And now our capacitor polarity, or the charge on it, will look like that. Then the charge on this one will look like this. I'm not actually sure if this is accurate with the converter topology that I took a screenshot of, but yeah, it should be. So if we have current going through here, right, you're going to have a voltage drop across this resistor and then another voltage drop across the capacitor. So when current's coming in, your voltage at this node is actually higher than the voltage on the capacitor, right? And that's why you have this bump up as our capacitor is getting charged. And then when current is going the other way, that is out of the capacitor, then you're going to have a voltage drop. So the voltage up here is going to be lower than that on the capacitor. And that's what this dip is. Now, the reason this is important is because you can see that this causes our ripple to be a lot higher. So over here is about 3 units. And then you can see if we have just, sorry, I didn't label these graphs because I just want to get the idea across, but we could do this with actual numbers. You can see normally, ideally, our ripple would only be 3 units tall, but now it's 4 units tall because that ripple is a unit tall and it adds and then subtracts. But yeah, the reason this is important is because when you have your power rails, like let's say we're powering one of our sensors off of a buck regulator, you have to think about how noisy can the power rail be, and this is adding more noise to our power rail. So if something's ever losing power, or you think that something on the other side of converter is pulling too much current, then this would be a good place to look. You would want to look at the switching waveform on the output of your regulator. Yeah, Barris, do you have a question?
Yeah, a small one. So in this circuit as well, the voltage source, it's an alternating source, right? So the use of the diode is only to regulate the direction of the current in that case. Is it right?
Yes, so this converter is actually a DC to DC converter.
Or is this
Uh,
DC?
yeah. Um, yeah, I guess I can go over the book really quickly just so um, it makes more sense what I'm talking about. But we will,
Mm-hmm.
this is a good topology and we will go over this more later. Oh, sorry, Drew, are you trying to say something?
Sorry, yeah, I was just like if so if this is DC to DC, then if we want do we need a DC to or do we need an inverter then if we want AC?
Yeah, so a DC to AC, that would be an inverter. Sorry, writing with the trackpad's not nice. And then AC to DC would be a rectifier.
Got it.
And yeah, those can both be, you can use diodes there to make simple versions of those, but we'll go over that when we go over the different types of converters. And now as I'm talking about this slide, I think maybe we should have done that presentation before we did this one, but it is what it is. There's some things later in this presentation that I thought should be covered before that one. But anyway, um, the way this works is basically um, you're gonna have, so let's say in the first state, the switch is closed. You're gonna have current going through here. Then you have a positive reverse bias on this diode. So this diode's basically like an open switch right now because we have this voltage source across it. Current is going to go through our inductor and charge that up, right? Because initially when you have a voltage across an inductor, it'll start charging. But if there's no current through it before, it'll resist changes in current. And then that current will go through, and some of it charges our capacitor, and then our capacitor discharges in the next state, and some of it powers our load. And now in the next state, when this switch is open, right, our source is disconnected. And then that will remove the bias on our diode. And then our diode will actually be connected because the current that was going through this inductor, it's not going to like that that switch just turned off. So it's going to keep pulling current as it slowly ramps down. And that current will come through the diode. And then that'll keep powering this system as the energy in the inductor slowly decreases. And then the capacitor is for filtering. So it has some ripple as well. That's what we have drawn over here on the left. But basically this switching speed, like how much you have it on versus off, is how you can determine what voltage you have across this resistor. Does that generally make sense? I'm trying not to get too much into the weeds because yeah, this is important to know. But yeah, like I said, we'll cover this in a different one. Yeah, Bears.
Another quick one.
Yeah.
So why does the bias on diode just disappear? Isn't it just a PN junction diode like stay like that? Doesn't it just stay like that?
Yeah, that's a good question. So the thing that changed is, so the waveform on the switch up here, it's gonna look like this. Sorry, let me finish drawing it and then it'll appear once I let go, I think, for you guys. So it's gonna be like on and off, right? So when it's on, like there, then you can think of this as closed, like it's a wire. And then that means that the battery voltage that's here is also here, right? Because it's a wire, so it'll be the same voltage. Now in the next state, when it's off, this switch gets opened. So it's basically like it's an open circuit. These two are not connected. So the voltage at this node is actually, it's like your inductor is going to be pulling current, right? So the voltage at this node just drops rapidly, and then it'll actually be lower than ground, and then the diode will turn on, and then basically it'll be ground. So the inductor is pulling a bunch of current, right? Because it was pulling current from the source, DS, and suddenly the switch opened, and there's nowhere else to pull the current from, but the inductor doesn't like that, so current keeps going and it has to come from somewhere. So it'll drop this node voltage all the way down until the diode turns on and becomes a short circuit.
Okay, got it. Thank you.
All right. Okay, so really the one of the more important parts that I want to get to, because this is may have already happened to you, but will eventually happen to you when you start working with boards, and I want to make sure you guys knew this for when you start powering things on, is let's take, for example, this schematic right here. This is the low voltage power distribution board like top level schematic in the schematic tree. So as you can see, we get this power source over here on the left. That's our low voltage batteries. And then we have our grounded low voltage fuse, which is required by the rules. It's the first thing that the battery power goes to, so that if too much current is pulled, it burns. But then the way we actually have it set up is we have sub circuit fuses. And that's so that each of these subsections, like the coolant pump, the accumulator fans, the radiator fans, and then the shutdown circuit source, if any of those individually pull too much current, only they can only burn their own fuse, and hopefully that should burn before the grounded low voltage fuse. And that like reduces damage, and also if it burns, we know what caused it. But inside of these green blocks, these are actually electronic fuses that we have. So these should shut off before these physical fuses over here actually burn. But what's actually inside of these electronic fuses? What do they look like? So here is the schematic that is inside of this sheet symbol. So you can see that VN comes in on the left, and that's unregulated. And then we have a diode here to protect the circuit if the voltage goes too high, that will clamp it. This is actually a Zener diode, I believe. So if the voltage goes too high, this will actually become a short circuit to ground until that voltage comes back down. So it actually can't go higher than, I think I have it set to 25 volts or 26 volts. And then after that, you can see we have a 100 nanofarad capacitor. Now, that capacitor is for decoupling, so that if there's any current spikes, it'll be smoothed out. And we'll talk about what decoupling capacitors are in a second. But if you think about this capacitor as initially it has no charge on it, right? We're going to say there's 0 volts across this capacitor when we turn the board on for the first time. That's going to look like a short circuit to ground, right? Because there's no voltage across this capacitor, and suddenly we're putting 24 volts onto that. So it's going to charge up really fast. There's going to be a really big current, and then it's going to settle down. And that current looks like this. It's called inrush current. So when this turns on, the capacitor looks like a short. You source a bunch of current into that, and then after that, you slowly exponentially decay until the capacitor is fully charged and your system is up and running. Now this image, I took it from the powering up of a high voltage DC system, which it's important for you guys to think about this in both contexts. This happens on our low voltage side and our high voltage side. It's much more dangerous with high voltage because this inrush current could fuse the airs together, like I talked about in the last presentation. And there's other things to think about as well. But basically, 100 nanofarads might not seem like a lot, right? But then you realize that once this switch closes, this 30 volt 15 amp NFET that we have, it's IC1. Once that closes, actually also remember that this schematic is incorrect. We have drain and source swapped here, and that's been fixed since I took this screenshot. But this 24 volts, it's going to go through R12, the sense resistor, through this MOSFET once the chip closes it. And then we have this 330 microfarad capacitor on the output. And that 330 microfarads is very large, but that's what this chip recommended we use to keep our power rails stable on the output. But that's not just on this one. We have 4 of these. So that's 4 times 330 microfarads plus 100 nanofarads. Now, in the face of 330 microfarads, the 100 nanofarads looks like nothing, so we can ignore that. But there's like, that's going to be like 1,000 340 microfarads, somewhere around there. That's a lot. And that's enough to pull an insane amount of current. And when we pull that much current, remember what we have at the beginning, we have these fuses. And that's definitely going to pull more than 15 amps. So how do we stop this fuse from burning and still turn on the system? Now, it's some of it is like an important thing to note about physical, like real fuses that burn is that they can take spikes of current. It depends how high that current is, it depends how long the spike lasts for, but that is an important thing to note that real fuses don't burn instantly as soon as you hit the exact number. It says on the data sheet like how long it takes to burn at what voltages, at what currents, at what temperatures. But this would probably burn that. So what the eFuse has is called a timer pin. And actually, I realized I forgot to put a screenshot. It's on the bottom of the chip. I only have a screenshot here at the top half. But the chip has a timer pin where it's able to like slow that inrush current and slowly open up the FET instead of just like instantly pouring everything in there. And that resistance allows you to charge a lot more slowly and approach the actual voltage that you want. So basically all of that is to say you insert a resistance to slow down your charging. Um, and it's using the MOSFET for that. Or I think that's how this one specifically works. That's not how they all work. Some timer pins just ignore faults for a certain amount of time. Um, and then you hope that your inrush current lasts less time than that. But yeah, is there any questions on this? It's something to be careful of because you guys want to make sure that when you power on a board for the first time, if any of these eFuse ICs were broken, you could possibly burn fuses if you pull too much current. That's why it's also a good idea to always set the current limit on your power supplies when you guys are testing these boards before you plug it into real batteries. Always test with a power supply first, and that way you can actually see how much current the board is pulling. And if it's too much, something might be shorted. But yeah, any questions? All right. So decoupling capacitors, I've been talking about these for a while, and I mentioned them quite a few times in this presentation. But what are they actually for? Basically, imagine you have a voltage source over here on the left, and you have your system over here on the right. There's going to be some trace that spans between those two, and every trace has some inherent inductance. I think Bilal said the number, like the rule of thumb is like 5 nanohenries per centimeter on a PCB. So you can calculate like about how much trace inductance you have. Um, this is actually a really big deal for when you're doing IC packaging because those pins are so small that they can introduce a lot of inductance into the system. So when you're, let's say it's a digital IC, it's digital ICs have lots of spikes, like it's up and down, right? Because it's zeros and ones. So they actually have very spiky waveforms on their power rails. So if you're switching on and off, then if you have an inductor, right, the voltage across the inductor is equal to its inductance times the change in current. So if I suddenly have a change in current where my digital node is switching from a 0 to a 1, and I have to charge that up, then you're going to have a voltage drop across this inductor. And then your voltage here, if we say let's this is like a 12-volt battery, your voltage here could drop quite significantly if your inductance is too large. So let's say your voltage drops because of this inductance to like, let's say it's really bad, like 9 volts, or maybe like somewhere between 7 and 9. If this system over here was relying on that 12-volt signal, and now you just drops that, things might start turning off. And let's say that's like the battery management system. You don't want that just turning off when it suddenly needs a lot of power, right? Because if you think about it, it just asks for a lot of power. It's probably doing something pretty important. So you don't want that to just shut off. So that's what the decoupling caps are for. You want to place them as close as possible to the power pins of your system so that when I pull some current and this voltage drops, because there's a voltage drop across the inductor, the current will basically be supplied by the decoupling capacitor. And then as the transient dies and this voltage, the voltage drop across the inductor isn't there, the current through the inductor will charge this capacitor back up, and then the inductor will continue powering the system. But basically, the capacitor helps in all transient events. So if you have something turn on for the first time, there'll be a voltage drop across the inductance because there's a big change in current. If, like I said, if you have a digital switching waveform, if you have a switching power converter, then you're going on and off. There'll be some drop when you start. So there's a lot of cases where this is needed. So it's always good to have decoupling capacitors on your power rails in order to smooth them out. Is there any questions on like what causes this or why decoupling capacitors are really important?
Are there specific values that we should calculate, or we can also have like, for example, um, more just to be safe, or does it have to be like a specific, um, like on the dot value?
Yeah, that's a really good question. And that's a great segue into our next slide. But quickly before I go to that slide, I was going to say something, but I forgot. I don't know. If it's important, it'll come back to me. Um, oops. Wait. Okay. So as you can see in this example of the chip, they have 10 microfarads, 0.1 microfarads, and oh, they have 2.1 microfarads. Actually, where did I put that graph? Okay, yeah, sorry about that. So, like I was saying, you asked why do we put, or what size capacitor do we put, and how do we determine that? So in order to explain that, I've come back to our equivalent series inductance slide because I wanted to use this same graph here. So this graph shows if you change the equivalent series inductance, but the same thing happens with the resonant point if you change the capacitance, right? Because that point is 1 over LC is where you have the lowest impedance. So if you imagine our noise is at some high frequency and you actually want to use capacitors of different orders of magnitude in order to get a graph like this, where basically if you have all these capacitors in parallel, right? And capacitance in parallel sums. So when the capacitance like drops off like this, it actually makes sort of this shape of like you have this, then it drops off, and then this one starts to have high impedance again. But now this one has low impedance. So you could actually just go down this path instead. And this one starts to go up, but then this one has low impedance. So you could actually just sink the transient into this step, and then they all come back up. So you can see it kind of gives us this like band stop filter where any transients in that frequency range will get taken out. And basically what that does for us is, if I can go back, is usually you put like 10 microfarads, 0.1 microfarads, and then like 100 nanofarads, I think, or maybe something a bit larger than that. And that's the standard values to get you like, or 0.1 microfarads is 100 nanofarads. Yeah, there's another value that's standard, but usually 10 microfarads and 0.1 is good enough to get you across, because these are large enough capacitances to source any current you need. But yeah, basically you want to pick a couple different values so that you can sync any transients across a range of frequencies. And having that capacitance drop off actually helps you here. Or it's not a capacitance drop off, it's a impedance drop off, because you have a, like, impedance is equal to 1 over j omega c. So yeah, basically the long-winded answer to your question is you want to pick a range of values at different orders of magnitude, and that'll help you deal with any transients at a large range of frequencies. And like I was saying, here you have an example of, this is a chip that has a bunch of decoupling capacitors on the bottom. And that's so that they can get so close that it's not even on the PCB, it's on the chip itself. And then this one on like this is like a computer motherboard or something. You have these bigger electrolytic capacitors that are supplying power to something, probably decoupling.
Got it. That makes sense. What's the chip that's shown in the schematic here? Is that just like a sensor or something?
Oh, I'm not sure. I just got this from the internet because it was a good photo
Okay.
of,
Yeah.
it just really focused on the decoupling capacitors. You could look up this
Yeah.
part number and
Oh
if you were
yeah.
curious.
Yeah.
AD is typically an analog devices component, so they probably produce this. I don't know what the ADXL 345 is though. Something digital. You see it has an I2C bus and then 2 interrupt pins. Oh wait,
Yeah. It's a
it has
accelerometer.
I2C pins, but this is a chip select and a serial data out, so it's actually
SPI.
5, I guess. I'm not sure.
Mhm.
Anyway,
Yeah. Apparently it's a 3-axis digital accelerometer.
oh, it's an accelerometer? Okay.
Yeah.
Yeah, typically those are like digital communication because transmitting that over analog would just be difficult and
Yeah.
unnecessary.
Right.
All right. Now, this is one of the more important things, and I want to spend a bit more time here. This is also our last thing, so we can go back and cover any questions. And I know this presentation was a bit shorter, so definitely if you have any questions, let's spend some time doing a Q&A at the end. But battery non-idealities. So typically, when you simulate a battery, it's not just the battery, right? It's not just a ideal voltage source. Um, you have typically people use the 4RC model if you want to be like super precise. So you would have this RO, and then you would actually have 2 more of these like RC in series. That would be 4RC, which is counterintuitive because it's actually 5 resistors and 4 capacitors, but it's called 4RC. So you would have 2 more of these blocks, or you could also count it as like 1 more of this added on right here before you got to your output. That would be the 4RC model. Typically, we use that for battery cell characterization as we're going into the system. But really, for the general thinking, the thing that I really want you guys to like get down and understand because it affected us big time last year, and I'll talk about it a bit more. And I want you to be aware of it for if it happens this year, is just this first resistor. There's some internal resistance in the battery, right? It's not just a voltage source. So that
Yeah.
takes places in like the actual internal chemistry of the cell contributes to that, and that's what it's actually talking about here. But also, if you think about it, there's some resistance in the bus bars that are inside of the segments. There's some resistance in the high voltage wire that is connecting the battery to the inverter and then the inverter to the motor. There's some resistance in the junctions between these components, right? When you have like the actual Energis module and then you have the bus bar touching that, that's not like a perfect conduction path. There's going to be some resistance because it's just two pieces of metal touching. They're not even fused. So all of that introduces different forms of resistance. And so what I want to emphasize is this graph on the right. So as blue is my current, so let's say I have a current event, like I'm pulling some current, and then suddenly the driver presses the accelerator really hard, and my current shoots up like this. Then across this resistor, right? Let me redraw the equivalent circuit over here so it's a bit more clear. I have voltage source, resistor, and then just to simplify, let's just say this is motor. Really, right, it goes into the inverter, and then the inverter does the control to do the three phases of the motor. But anyway, let's say this is our 600-volt battery. When the motor, the driver suddenly presses the accelerator, and the motor takes a bunch of current in, it's going to be a voltage drop across this resistor, right? There's some current flowing through resistance, there will be a voltage drop. But you might say, these are really small resistances, right? It's like, oh, this is just a slightly non-ideal system. How much would it actually affect me? So I did some napkin maths down here for you. The resistance in a new 18650 cell, like the typical resistance, when it's only been cycled one time, and this only gets worse when you get to about 50 cycles, it's actually double this, it's around 100 milliohms, at least in the data that I found. But let's say most ideal case, these cells have only been cycled one time, 50 milliohms of resistance. You actually can reduce that number by 4, right? Because we have 4 cells in parallel, and resistors in parallel do divide. So that's actually pretty good, right? We got down to, oh, sorry, I wrote this wrong. We got down to 12.5 milliohms. I'll correct that. And then if you take 12.5 milliohms, oh, but then we have 140 Energis modules in series. Oh, well, that's okay. It's only 1.75 ohms, right? Well, let's say we hit that max fuse limit, which we're even limited right now at 60 amps, right? Because the fuses in the Energis modules are only low voltage rated and they're 180 amps. So the rules actually say we need a high voltage rated fuse at the whole pack. That's a third of that value. Just some rule stuff. That's why we're trying to go to custom cells next year so that we can get a bigger fuse because this is actually one of our biggest limiting factors. But let's say we pull the max that fuse at 60 amps, which is very common. We do pull 60 amps quite often when you're accelerating. Times 1.75 ohms. Wow, that's 105 volts. So at this node, you're going to see 495 volts. That's a lot less, right? That's that's a scary low number. So the issue you run into is what's the minimum operating voltage of the inverter? How low does that voltage go before the inverter shuts off? And the answer is a lot higher than we would like it to be. The issue we ran into last year is the aluminum casing for the accumulator, right? Aluminum warps a lot more when it welds. And it was our first time doing those long pockets, right? So we could actually only fit 4 out of the 8 segments in there. So our total battery voltage peak was only like 300 volts or something, because it was only half, right? Somewhere around there. So when we would pull 60 amps and we would drop 105 volts, we were already limited. We were only like, let's just say it was 300. And once again, that's 300 volts at maximum charge, right? The discharge graph looks like this, right? Like it's kind of S-shaped. And then your average is like 3.6, right? Nominal. So 300 is actually at this point. So what was happening is we were getting to like this point where it starts dropping off here. Really, we want to operate until this lowest point, right? But we're getting to this point over here where it's only like 240 volts left in the battery. And oh, you press the accelerator too hard and that drops to like, what, that'll be like 135 volts. And then the inverter browns out. Browning out is when you lose power. Right, blackout would be like if you turn it off. Brownout would be when you pull too much power so it shuts off. So the motor would shut off because it would be like, hey, the high voltage system isn't charged high enough. It's not safe to be doing that anymore. But the voltage wasn't, well, the voltage was actually that low, right? But it was because the resistance, like we were able to source that much current, it could have kept going, but the system shuts off because it's like, hey, your voltage is too low. So the car shuts off. That's not good, right? If it's shutting off with like 30% left because we're browning out, then during endurance, we like are losing 30% of our capability on the bottom side. So you have to like way oversize it, which we don't want to do, right? So part of that is you can implement software limits so that if your voltage gets too low, you limit how much current you can pull, and that keeps your car operating right. We want the least number of unexpected power offs that we can have, right? We never want this thing turning off without being unexpected. We always want it to only turn off when the driver says, hey, it's okay for you to turn off now. Or if the car's like, I'm done, like there's no power left. The other way to help solve this issue is just reducing the resistance in the pack. You can actually like, if you take the bus bars and you just sand them all and make sure they're like shiny and clean before you assemble it, you can actually reduce the resistance by quite a lot. Um, that's actually something that we assembled our first segment and it had quite a lot of resistance. And then we just sanded them down and then reassembled it. And it's like, oh wow, it's like 2 ohms lower, which is like a lot here, right? But yeah, reducing resistance at every single spot is critical. Also because this isn't even getting into like power is equal to I squared R. So this is like how much your uh, stuff will heat up, right? So if we're at 60 amps squared, so 360 times 1 ohm of resistance, that's 360 watts you're burning. That's a lot. We don't want to be burning 360 watts. So you want to reduce that number as much as possible. That's also why we run like high voltage, low current to try to reduce heating losses, or at least that's the idea, that's the goal. Um, but yeah, I guess does this brownout idea make sense? I just want to make sure that I really hit it home because it's a really important idea, not just for this, but both it's important for high voltage and low voltage and formula and non-formula. It's really just an important idea overall that comes up a lot. So I just want to make sure it's really clear.
Yeah, so essentially at a very, very high level, a blackout is when there's a deliberate like power shut off.
Yeah.
Okay, and brownout is when something draws so much power, again, like at a very high level that it basically just goes to zero.
Yeah, that's correct.
Okay.
That's why, like in LA, we get a lot of brownouts, right, during the summer and early fall. When it
Yeah,
gets so hot, everybody turns on their ACs, and then the
right.
grid pulls too much power, so it shuts off as a safety
Yeah, yeah.
feature.
Okay. Okay, that makes sense.
Yeah,
Yeah.
yeah. So I know we covered a, a pretty decent amount of some pretty dense stuff. So this is all the material I have right now. I just want to give you guys some more time to like, if you have any questions or if there's any parts you want to go over again or talk about more in depth. Um, I want to leave the floor open for that because I really didn't make that many slides because I want to make sure that you guys understood everything I was talking about. And of course, I know questions come up like later as well. Like maybe you're looking back at this and have more questions. So of course, Slack is always open, but I want to leave the floor open now if you had any more questions about or wanted to go over anything again. All right then. Definitely make sure to follow up on Slack if you have anything. But I think I'm gonna end the recording here. So thanks everybody and see you at the next one.